So good afternoon, sir. Today we have our first technical talk by Professor Tapobrata Som. Professor Tapobrata Som, he is a professor of Institute of Physics at Bhubaneswar. He has varied research interest. He has varied research interest like ion beam induced self-organized pattern formation and their nanoscale functionalization, thin film growth and characterization, hole blocking solar cell, application of memory-restricted devices for minimum computing, and a lot of things. Professor Som is presently a leader of electron cyclotron ion source-based low to medium energy ion beam facility since 2012 and surface nanostructuring and growth laboratory since 2009 at IOP Bhubaneswar. Professor Som received his PhD from IIT Kanpur in August 21. He joined as a senior lecturer at IOP Bhubaneswar and he became a full professor in this same institute in 2016. During this period, he has been a mentor for 10 PhD students, 20 postdoctoral fellows, and during his 30 long years of experience in physics research, he has published more than 200 research papers in several reputed international peer-reviewed journals. And his edited book on the nanofabrication by ion beam sputtering, fundamentals and applications called Bible in this area. He has also been a guest editor of several journals. He is an excellent executive body member of Ion Beam Society of India. He was the chair of International Conference on Ion Beam Induced Nanostructuring of Materials 2011, local organizing committee member of huge number of international conferences. I cannot speak here. He is an international scientific committee member of biannually organized international workshop on nanoscale pattern formation at surfaces. Besides this, he is a member of Accelerator UJS Committee of IUS in New Delhi and a member of the Technical Review Committee for DST EST Solar PV Photovoltaic Hub in IST Singapore. With this very short introduction, I like to invite Professor Som to take the charge of the sessions and transferring the screen to Professor Som, sir. Before that, I just like to say another few lines I like to add about our personal introduction. Whenever I feel depressed and whenever I feel fully disbalanced, that time I usually call Professor Som sir and I get some energy from him. So I believe all of you will get very good session from Professor Som sir. He has 3 talks already scheduled always with you, and I'm very much sure you will get benefit. So with this, please, sir.
Can you see the screen, please?
Yes, sir.
Okay.
It is full screen, sir.
Okay. So thank you so much for kindly inviting me and for the introduction. It's a huge pleasure to be there with fellow colleagues from different places and also with the colleagues from NIST. So at the outset, I would like to wish you a very good afternoon and or maybe still we are in the morning session. Yeah, very good morning. And I have tried to make a balance to make it quite informative with the colleagues and with your students and the young postdoc fellows. I have tried to avoid showing you or going through very complex equation solving and all these things because of obvious reasons. Because instead, I had, in spite of the fact that the pattern formation process that I'm going to talk about does involve a lot of mathematical. Actually involved a lot of mathematical component, but still my intent will be to share with you and introduce you rather because I'm pretty sure many of you are not belonging to this area and so a fair amount of interaction probably will be of more interest for all of us. I would like to tell you that although it would be nice to have questions, but one at a time will be better. And if you don't mind, the best ploy for both the speaker and the organizers will be to take questions at the end. Nonetheless, if you have really something interesting to ask me, please feel free to stop me and ask your question or whatever comments you have to make. With this, I would like to thank Dr. Panda once again to invite me and to give me this opportunity to share our results and my long experience with the colleagues and the young crowd present in today's online short-term training program on recent trends in emerging devices and nanotechnology phase 1. And I must also appreciate Professor Panda's effort to hold this series of these modules, and particularly in this really very tough pandemic situation. But at the same time, it goes beyond saying that such meetings probably give us a much opportunity to go out of our box, because not much is happening. We, the humans, are of course social creatures, and this socialization or any kind of entertainment which keeps us going is almost stopped for months together, more than a year, so nearly heading towards 1.5 years. So at least we are blessed to be academicians and get to sit down together across the state boundaries and sometimes the boundaries of our country. So I have special appreciation once again for Dr. Panda to organize this meeting at a very tough time, which is indeed a pleasure to see and so many colleagues and students to be present, particularly the young minds. I understand the young students as the mostly suffering a lot. We all are there with you, but yes, the kind of insecure feeling, the kind of uncertainties that this very tough time has created, which is unforeseen. The world has come to a complete halt almost, apart from some few exceptions. So, and all we can hope is the good days will be coming in few months' time, or maybe in a year time, or sooner the better. And for that, everybody has asked, and we are now quite well versed with the SMS message, and with this masked condition, we have to probably move ahead, and we should expect that we can interact more in 1:1 situation instead of this so-called online mode, which really is a very different platform where we can see each other's face. Indeed, that's the pleasure. The meetings are more intense. The presence of the number of participants I am seeing over the last 15 months is very good, rather than physical meetings. But nonetheless, physical meetings are important, and communication through, human-to-human communication is, of course, most important, which we are missing. Let us now start talking on the subject matter. What is a pattern?
Sir, is it possible to switch on your video, sir?
Just 1 minute, but yes. Is this okay? I think I'm visible, correct?
Yes, sir. Thank you, sir.
Yeah. Okay, so let's start with the very fundamental thing. What is pattern? Okay. A pattern originates from the French word patron, and is a type of theme of recurring events. Just 1 minute. how to get rid of these participant kind of frame devices? Any idea, please? Can you please let me know? Because I'm seeing this these few participants in a box which is actually overlapping with my data, I mean presentation slide. So any idea how to get rid of that? Devasis, are you there?
Yes, sir.
Yeah, I mean, I'm getting this thing. So, okay, now it's gone. Okay, fine. Okay, sorry for this interruption. As I was talking about, a pattern is a type of theme of recurring, events or objects, which is sometimes referred to as elements of a state of objects. And these are all very natural things. You see, this pattern on the left hand side is actually a painting which is seen at Sheikh Allah Mosque at Isfahan in Iran. And what a beautiful pattern. And this is not only the case of this Iranian mosque. We get to see at many other mosques and old buildings May I request all the participants to please mute yourself? So, and you see, interesting thing is these elements repeat in a predictable manner. It can be a template or a model which can be used to generate things or parts of a thing. Okay? And here in the middle, we have another pattern. It's a reaction diffusion like pattern. I will show you that such a pattern is possible to replicate, okay, using ion beam irradiation on a material. Okay, and this we all know these are frost crystals found on cold glass. Okay, now there are more mesmerizing patterns, natural patterns, and these are all macro scale patterns, very large scale. Goes beyond saying that almost everybody of us have seen these kind of sand ripples, no matter whether near around sea beach or in a desert. And these cloud patterns, every now and then we get to see and particularly when we keep flying, it's maybe 9-10 kilometers above the surface, we get to see in the sky these kind of patterns, the cloud patterns, and then these zebra patterns. It looks almost like a ripple pattern, a broken ripples kind of things, almost similar with these sand ripples pattern. And these are zebra pattern, and this far also is from the leopard. So these are all beautiful patterns, and they may not be exactly same, but there's a huge similarity that how they propagate. And then interesting thing is this kind of ripple patterns that we get to see in sands and deserts. This can be replicated if we consider these tool of energetic ion beams. And when we say energetic ion beams, we will slowly come into the other examples slowly. Actually, we'll get to see most number of examples here, just to get a fairly good feeling that the possibilities and restrictions of these kind of pattern formation using the ion beams. Now, here the scale bar I've kept similar. Okay, practically I borrowed it from this article, which is now nearly 15-year-old. What is seen on the left frame is the ripples on sand. It's taken from a snapshot from the Gobi Desert. And here we get to see ripples on surfaces artificially created. Basically, a silver thin film was subjected to the ion beam, energetic ion beam, to give rise to such fascinating ripple patterns created on a silver surface. The difference in between these two frames over the same length scale, the same line length of line bar is the different length scales involved here. For instance, this much, this line, the length of this line scale, the scale corresponds to 1 meter for these ripple patterns, saying in sand, whether it is of 50 nanometer. When you talk about the silver surface that artificially replicated pattern, ripple patterns, as we talked about. And then the question is, what is self-organization? Self-organization is the spontaneous and often seemingly purposeful formation of spatial, temporal, or both spatio-temporal structures or functions in systems composed of few or many components. Self-organization is a process where some form of overall order arises from local interactions between parts of an initially disordered system. Self-organization is realized in physics of non-equilibrium processes and in chemical reactions. Particularly for chemical reactions, it is often described as self-assembly. However, the self-assembly term is quite popular in case of molecular beam epitaxy grown specimen, where few monolayers are being talked about. And so it's being seen from chemical reaction when we talk about the laboratory scale experiments. One of the examples, the sand dunes arise from a sand deposition behind a small wind shelter. This increases the wind shelter and accelerates further sand deposition. A clear self-enhancing reaction. However, sand deposited at one position cannot collect somewhere else. Now, very important technological revelation has now made it almost mandatory to have sub 100 nanometer patterns. It's very, very important, I tell you, because of the seemingly important aspect of downsize of devices, electronic devices. Everyone wants it in few nanometers scale, length scale. And then one has to talk about a large number of devices, all to be integrated with that. And the conventional photolithography is widely used for microelectronics and other micron scale devices. The advantages are arbitrary pattern design can be done, and it yields high throughput, and also it involves relatively low cost. However, disadvantages are wavelength of the light imposes a fundamental limit, and hence it becomes difficult and expensive to make devices with a feature size less than 100 nanometer. So then one needs nanolithographic techniques to produce sub 100 nanometer, particularly sub 10 nanometer features. And the most befitting technology that actually in today's data are available, namely E-beam lithography and X-ray lithography technique. So EBL, that is the short form of electron beam lithography, is limited by serial processing nature, however, while X-ray lithography is very, very expensive and it needs nothing less than an X-ray synchrotron facility. So it requires new techniques. Now the question is, can ion beam help us? Ion beams, remember, are very, very important component or processing tool for the present day devices. Any electronic gadget needs some integrated circuit to large scale integrated circuit to very large scale integrated circuit to ultra large scale integrated circuits. And all these circuits, they require large number of components, electronic components integrated with that on a small chip. Thereafter, requiring a large number of processing steps where ion implantation and ion beam processing in general are very, very and play very, very crucial roles. Starting from doping in semiconductors to phase synthesis for creating the interconnects and the contacts to form embedded nanostructures and so on. Ion beams are really, really very important. Now, ion beams offer high spatial selectivity, meaning wherever we want to take the ion beam in a particular target material, we can do so by choosing the ion species, ion energy, and some other parameters properly. It offers a relatively low temperature processing, and it's not governed by equilibrium thermodynamics, which is quite win-win situation to create self-organized patterns. And any ion beam can be used to be introduced in any material. For instance, there is no restriction whatsoever to put gold into thorium or thorium into carbon and so on and so forth, and uranium into gold or whatever. Any element in the periodic table, if we can generate the ion beam, stable ion beam, then that species can be introduced, can be implanted in any other material. It's a brute force method. As energetic object, particles can get into directly into target material. And with the advent of focused ion beam technology and low energy, high current broad beam ion source, one can achieve sub-100 nanometer feature sizes as well using ion beams. Okay. Now, focused ion beams can produce regular patterns on small areas in general, although not restricted to pattern large areas over a very long time. And throughput is also very low. Well, broad beam ion sources can create patterns on large areas, fast but not very regular patterns on every occasion. Now, this is a very fundamental slide on how an energetic ion interacts with the solid. Okay. Whenever an incident energetic ion beam enters the solid, we can expect several phenomena to happen, several processes to happen as the ion starts penetrating within the target material. There will be backscattered ion, there will be sputter atoms, there will be reflecting ions, okay, and so on and so forth. As a part of the secondary collisions, there could be emission of photons, X-rays, electrons as well. And there could be vivid formation of damaged areas within a crystalline target, for instance, as shown here, okay, but through this elliptical area. And this place can be getting completely amorphous as well if the damage is very severe. There could be a complete disorderedness in a highly crystalline target. So ion radiation introduces energy, giving rise to target damage, atomic redistribution, sputtering, and so on and so forth. Next, one of the components is very important to understand is ion patterning process, and that is sputter erosion. In other way around, ion beam sputtering. Question is, what's that? As is shown through the schematic diagram, we get to see that when an energetic ion beam traverses a certain depth in a target material, whether the ions will come into complete halt, that is indicated as the term RP, which is known as the projected range. And when you keep adding such small trajectories within the target material, altogether that will be the range of ion in that particular target. And then when we get to see these sputtered atoms, then one should ask this question: how does it take place? So erosion of surface atoms by energetic ion bombardment is known as ion sputtering. Here, I mean, in this process, physically the surface atoms are removed by binary collisions. Important thing is, it sets the limit of maximum concentration of atoms that can be implanted. Why? Let's think of this situation that it is shown here. Suppose we talk about very low energetic ions. The physics remains the same. Because it depends on the ion energy and the target material. For a given ion target combination, how much it will traverse, it depends on the ion energy. Of course, incident angle and other couple of parameters will also be influencing this, but more or less, mostly it depends on the target material as well as the incident ion mass and its energy. Now the question is, think of, as we keep on bombarding, ion implantation will continuously be taking place. Okay, and for a given ion energy, it should have a projected range of RP. But then, simultaneously, these sputtered atoms will also be present. That means this ion sputtering will continuously be taking place. So this is the physical erosion of a target material. So target atoms start getting lost as well. The target atoms physically start getting lost as well. What does it mean? The surface will not be here across this pink line. The surface will be dynamically moving downwards towards the depth. So what will happen? This way, the projected range for the first set of implanted atoms, ions, can be completely eroded. Okay, so the implanted atoms may be possible to be seen, and that is what this set. I mean, we talk about setting up of the limit of maximum concentration of atoms. So it's not that we keep on bombarding and keep on introducing these implanted atoms in a target. Okay. The limit is set by the sputtering phenomenon. And as I told you, mostly it is dependent on ion species, energy, and target material. How to calculate this sputtering yield is number of sputtered atoms per number of incident particles. So the mean number of emitted atoms per total number of incident particles. Per unit area maybe, which is known as ion fluence. Now, due to ion sputtering, what can happen? You know, I mean, if we talk about any ion bombardment process on a material, generally it is known that any material will be having a rough surface, will be having some roughness. And when such a surface will be subjected to ion bombardment, then there could be surface smoothing. Okay. There could be roughness enhancement as well. And balance can lead to the formation of periodic structures, other way around, the pattern formation. Now, let me tell you that nanoscale pattern formation by energetic ions actually depends upon a lot of experimental parameters. For instance, patterning depends upon ion energy, angle of incidence, ion fluence and flux, ion target combination, sample temperature, substrate rotation, impurities, etc. Give me a few seconds. I need to take some water. And it's important to know that patterning, that is this self-organized pattern formation due to energetic ion bombardment, is observed on semiconductors, insulators, metals, or even on polymers. Almost all kinds of materials, we can generate such patterns. Only thing is that we have to keep in mind several experimental parameters. Means these parameters, which are listed here, they may give rise to very different combination of patterns which may evolve. So depending on all these things, one can form a gamut of self-organized nanostructures on several material surfaces. For instance, I have shared here different and beautiful patterns that are generated in laboratories. Some are by us. The many of these patterns have been successfully generated by us. And some were reported by some other groups as well. You get to see here that the leftmost frame, where we have written ripples, is per pseudonym the silicon surface, using very low energy argon ions, 500 electron volt of argon ions. Here we have utilized sub keV ion energy, 500 eV. We have also gone up to 250 electron volt of ions. And what we are seeing here, next frame, That is again the same ion energy, same sample, but the incident angle is different. We get to see these beautiful facets, nanoscale facet formation on the same sample, under same experimental conditions, but with only one change, and that was the angle of incidence of these ions. For instance, this leftmost frame utilizes an angle of incidence of 60 degree, and how it is defined is shown here. So with respect to the surface normal, the incident beam direction makes an angle theta, which we talk about 50 degree or 60 degree or whatever. On the other hand, these facets were formed corresponding to 500 electron volt of silicon ion bombardment, argon ion bombardment on the same silicon surface, but at an incident angle of 72 degrees. And we get to see gold ion bombardment can give rise to beautiful crisscross patterns. You recall the first slide that we talked about. I told you that this we will replicate and show in a later slide. So this is that. And then wonderful checkerboard pattern formed due to argon ion bombardment on germanium. Here the angle of incidence are different, and the fluences are also different. That's why I told this parameter, variation in these parameters will play a very important role in terms of pattern formation. Now I'll start showing you a lot of examples. As I told you, this is the first case where, depending on the variation of this incident angle, we get to see various patterns on silicon surface. For instance, at an incident angle of 65 degree, we get to see these patterns, ripple patterns. Then 80 degree, we also get to see rotated ripple patterns, okay, needle-like structures. And 82.5 degree incident angle, we get to see a flat surface, nearly a flat surface. So ripples evolve in silicon actually from an incident angle of 51 degree. And transition in ripple orientation with respect to the projected beam direction takes place at an angle of incident angle of 80 degree. So ripple wave vector becomes perpendicular from parallel one. Changes its directions. Very clear here. As we move from A to B. Now, here we talk about germanium. Example of germanium with 250 electron volt of krypton ions. Okay, this is not our work, it's a work from Harvard University. And you get to see from this parametric phase diagram, this is nothing but a E theta phase diagram, E theta diagram. E is the incident ion energy and theta is the incident ion incident angle of incidence of the ion on the target. So these also that at which angle for a given ion energy, what are the patterns that we generate? It's very clear that up to an incident angle of nearly 758 degree, there is no pattern formation. It remains flat, stable surface. And then we over angular window of nearly 57 to 75 degrees or so, we get to see parallel mode ripples. What is parallel mode ripples? Where the ripples are running perpendicular to the ion beam direction. The example is shown here, corresponding to incident angle of 60 degrees. Very interesting. Although for silicon, we had seen here a lot of pattern formation for germanium, similar ion energy and ion species doesn't give rise to any pattern formation. The moment we start applying some high temperature to the sample during the same argon ion implantation, which otherwise does not give rise to any pattern formation as is seen from here and is stated here, no pattern formation by argon ions in germanium, and it remains so up to 250 degrees centigrade. The surface remains flat. What I mean when I say stable surface in the context of ion patterning, I mean that the pattern formation remains absent. So you see, from up to 250 degrees centigrade, interestingly, the surface remains flat and stable. The moment we increase the temperature by 10 more degrees, we start seeing the checkerboard pattern formation. And we increase the temperature up to 320 degrees centigrade, the checkerboard pattern gets dimensionally enhanced. And at 430 degrees centigrade, this inverse pyramid formation takes place. Very rich physics is involved in it. Not getting into those details and those calculations, let us now get into some compound or mixed semiconducting phase of silicon and germanium. It's a very, very important alloy for device physics. And Si.9, G.1 composition was considered when they were explained in terms. We get to see from 50 degree, we vary the incident angle to 50 degree to nearly 70 degree or so. Some isolated island structure formations got initiated at 50 degree, but then at an incidence angle of 70 degree or so close to that, we get to see beautiful ripple pattern formation. Likewise, let's consider the case of gallium arsenide. We get to see that for theta is equal to 0 degree, and for the given fluence, ion fluence is number of ions actually hitting per unit area. That's ion fluence. And number of ions hitting an unit area per unit time gives us the ion flux. Okay. So by varying the ion energy, this Chinese group reported that dot pattern formations do evolve. However, this could not be reproduced not only by us but many other groups as well. At a much later study and using much lower energy, an order of magnitude less energy, in the tune of ultra low energetic argon ions of 30 electron volt only. So that an incidence angle of theta is equal to 0 degree and nearly comparable ion fluence. It was reported that beautiful ordered patterns are possible to be formed on gallium arsenide surface at, for normally incident ion beams. And these ripples, ordered ripples, evolve at a temperature of 450 degrees centigrade during irradiation. And this has been attributed to the early soluble barrier. I'm sorry for this mistake in spelling. This last E should be actually interchanged with the L. This should be swaddle. Anyway, so but for little higher energy, we get to see, for instance, at 500 electron volt of argon ions, when you consider an incident angle of 65 degrees with again comparable ion fluence, we get to see a flat surface. Now let's take the example of another compound semiconductor in the form of indiumphosphide. Okay, at 0 degree incident angle, the dots are formed, while the other authors have reported that using 5 kilo electron volt of nitrogen ions at an incident angle of 41 degree or so, with an ion fluence of 1 into 10 to the power 19 ions per square centimeter. The nanocones are formed. Very nice nanocones are formed. So nanodots are formed at normally incident ions, whereas cone-like structures evolved at oblique ion incidents. Now this is actually a paper in Science in 1999, which gave a huge boom to this field. When this German group actually bombarded gallium arsenide target by argon ions and at using different ion energies. And we get to see that for a similar ion fluence of 2 into 10 to the power 18 ions per square centimeter, we can vary the dimension of these dots, those are formed. And short range hexagonal ordering is observed, and conical dot size increases with ion energy. We have seen that smoothing of the surface you see, smoothing of the surface can take place as well as roughness enhancement can take place. So smoothing can take place if we have the roughness at the surface. At the same time, we can have diffusion as well, surface diffusion, ion-induced diffusion as well, which can actually give rise to this smoothing. But at the same time, we will have sputter erosion, which will physically create a local roughness. And if this becomes a cumulative effect due to large number of ions falling on the target in a random manner. Okay, so can you hear me?
Yes, sir. Sir, I think some network issue is there. I think your voice is cracking sometime.
Okay, now?
Now also, sir.
So maybe I take some water also just to reduce the human part aspect. Is it okay now? Even if it is not, I mean, I hope Devasis you are recording. So probably the visuals are will be remaining with all of us. Okay.
No, okay, sir. We need to switch off your video. Please continue, sir.
You see, that's what I have switched it off in anticipation of this network problem.
Yes, sir. Yes, sir. Sure.
Okay. But if it is extremely needed, please let me know. Okay.
No, no,
For
no.
your
Initially,
appreciation.
it's okay. It's okay.
Yeah. Okay. Okay. And so it's a competitive process in two competitive processes, mostly ion sputtering and ion-induced surface diffusion, that give rise to such pattern formation, and then that is the common belief by now after 20 years. And you see various patterns. Again, gallium arsenide is not restricted to only dot patterns. If we do, these are all at normally incident ions. But the moment we get into oblique incident ions, this argon ions only, but with little higher energy up to 7 kiloelectron volt, and incident at an angle of incidence of 40 degree, we get to see this kind of ripple patterns, pretty well ordered. And these small bamboo stick kind of patterns arise in case of indium antimonide. And here these patterns are all formed at room temperature. Still, fantastic ordering is visible. These are little older works, but only shows tremendous possibility. That's why I preferred to have these visual things more ahead of these mathematical equations and so on and so forth. Because getting a feel is very important. Getting a feel is very important rather than getting indulged into lot many equations, so then it becomes little abstract and we start losing our mind and soon get bored in terms of experiments. To have a best feel, it is very important that we gauge into these large number of visuals, okay, pattern formation which are reported in various materials. So here is the example of 1 kb argon ion bombardment in an important 2,6 material, cadmium zinc telluride, ZNTE. And the right frame is an example of 4 kV argon ion bombardment on halide material, potassium bromide. Okay. And now is the turn of metals. Metal doesn't remain behind. So, for instance, here we are talking about pattern formation on nickel thin film using 5 kV argon ion at an ion fluence of 1.8, nearly 2 into 10 to the power 16 ions per square centimeter. And formation of small nanodot-like objects turn into ripple patterns from 50 degree to 70 degree incident angle, and very mature ripples are formed. Okay, where the ion projection is parallel to the ripple orientation at an incident angle of 80 degree. And by using ion energy of 800 eV argon and with 2 orders of higher magnitude at an angle of incidence of 82 degree. Again, some other group had reported the ripple formation at 82 degrees, and using copper ion also. This was this was not for nickel, this was for gold, and this is for copper. But the important fact is, using energy in the tune of few hundreds of electron volt to a couple of keV, and using different ion species, and mostly not ion species, using different target material, using the same argon ions, people had reported nearly similar results of ripple formation at very high incident angle. But for silicon, if you recall, we saw ripple formation at a much lower angle. Okay. Now, these are the examples of aluminium target. Again, ripple patterns are seen. I mean, transition of the ripple orientation is very obvious from 40 to 85 degree. You see here the ion beam projection is along this arrow, and these ripples were, direction of ripples were perpendicular, but here it becomes parallel as the angle of incidence start increasing. Okay. The lower frames correspond to pattern formation using same energy of argon ions, but on cobalt target. So across the metals, so as I told, perpendicular mode ripples, where the ripple orientations are parallel, those are perpendicular mode ripples, and ripple orientations are perpendicular, that are parallel mode ripples. This transition becomes almost obvious for semiconductors as well as metals as well. Okay. Again, wonderfully ordered ripple patterns we get to see here. Okay. And this we see for platinum. But the important difference here, in contrast to the previous slides, is here again, the pattern formation is taking place at elevated temperatures. Okay. So in general, besides ion sputtering, diffusion of add atoms at higher temperatures generated by the ion impacts plays a crucial role in regulating the ripple separation in metallic systems. This is very important. So wherever we saw checkers pattern on germanium, we saw it at high temperatures, and these beautifully ordered ripples on metal surface also take place at elevated temperatures. And this is mostly due to, I mean, can be attributed to early swivel barrier, which actually is very popular term, or energy barrier that is being faced in case of molecular beam epitaxy related growth. So additional diffusion barriers, basically additional diffusion barrier that gets created or offered or encountered by a surface atom when it crosses an atomic step. Okay, so it's kind of step diffusion. I'm not getting into the detail. I mean, you can find out very easily through the search in the web and Google search or whatever, Wikipedia. You get to see tons of articles there. So it's basically the effects of an atomic state on the diffusion of atoms on the surface, which can be represented by the diagram below, which illustrate the potential relief pattern close to the step. We'll skip this slide. Now, what we see here is pattern formation on SiO2. Now I'll show you several examples of oxide materials. Well, I mean, this is, I introduced the slide. Now it is a published work, of course. I mean, this was published in Journal of Physics Condensed Matter. One of my past students, we did this work. I mean, this is 500 dB argon ions. Okay, and from a very low incidence angle of 35 degree to 80 degree, we get to see a stable surface at 80 degree, whether elongated nanostructures were formed in 70 degree, and ripples were formed up to 69 degree, 68 degree or so. Now, it's the turn of TiO2. Here, 800 electron volt of argon ions were used and 500 electron volt of xenon ions were used. So left frame and right frame respectively. And we get to see at high incidence angle parallel mode ripples. That means you can see, the direction of the ripple orientation is actually parallel to the ion beam projection. Okay. And the combination of preferential erosion of step edges and ion beam induced surface roughening actually can once again be attributed as to result in the surface morphology with nanoscale ripples aligned parallel to the ion beam. That's the perpendicular mode ripple. Okay. But here it was at 68 degree as expected. I mean, these perpendicular mode ripples where the ripple orientation is parallel to the incident ion beam direction happens only at higher incidence angles. This is the case of Al2O3. Again, parallel mode ripples are formed at 55 degrees itself, and perpendicular mode ripples are seen at very high angles as expected. Here, actually, ion beam induced viscous flow also plays an important role, which has been reported. Okay. Then comes the example of magnesium oxide. So this is another example where ripple formation is possible. Okay. And nothing new, but at 0 degree incident angle, dot formation was taking place at 1000 degrees centigrade. Whereas at 50 degree incident angles, these authors reported on ripple formation. Okay, perpendicular mode ripple formation. That means ripple orientation was perpendicular to the incident projection of the ion beam. Sorry, projection of the incident ion beam. And here is the example of zinc oxide, our own work we are here to publish. Beautiful ripple patterns are observed. First, the relief structure, dot-like elongated dot patterns, and then ripple patterns. And then with xenon ions and argon ions, we get to see the difference. The ripples are pretty matured. Okay. You know, exotic pattern formation is also possible to be seen when we intentionally introduce pattern, during the pattern formation, we introduce impurities. And you see, here the target is silica, and energy was chosen to be 5 kilo electron volt. Okay. And during this xenon ion bombardment, simultaneously, an iron foil was kept near to the ion beam, so that it was continuously sputtering. It continuously sputtered the iron atoms, which easily got introduced into the target atom, target material. And it led to very exotic patterns, which is otherwise very difficult to form. So the introduction of take-home message is the introduction of a second component can sometimes do havoc. See, this is oxygen ion induced pattern formation. Okay. This 8 kb oxygen. This is effect of impurity, and this is iron, 36 kb iron ions at 60 degree. Both in case of silicon. And you see, the iron actually get accumulated near these tape edges. Okay, these ripple, these valleys are formed, no? So you see, this look like almost the copy beads. So at the side walls of these tapes, and these tapes are these ripple patterns. Okay. So we are seeing it's a cross-sectional TEM image. So this kind of sense of ordering can also come. That's what I was telling. I mean, more such examples of our own work will be shared in the next lecture. And now we see the effect of silicon impurity in silicon. The same Harvard group had done. Okay. What we see here is the pattern formation in silicon at an incident angle of 65 degree for for xenon ions. The difference from left to right on the top frame is the increasing ion energy from 5 kb to 20 kb to 35 kb to 60 kb to 140 kb to 180 kb. So 36-fold enhancement in energy took place that led to nearly an order of magnitude enhancement in the ripple wavelength. Lambda is the wavelength and h is the amplitude of the ripple pattern. So amplitude also enhanced by nearly 20 times. And if we summarize the result for this particular work, we get to see that the amplitude linearly increases. Amplitude linearly increases with increasing ion energy. It's a very important observation. And now, very quickly, I'll try to show, since we talked about these enhancement in ion energy here, okay. So what happens actually for the argon ion induced pattern formation for silicon at a relatively higher, 5 times higher only ion fluence, okay, and we get to see the similar formation of ripples as we saw here as well, and at the comparable energy range, okay, 60 kV and 35 kV, 30 kV, and like that. So higher ripple wavelengths are easily observed compared to that seen for lower incident ion energies. Now this is the example of germanium. 60 kb argon ions lead to the formation of very feeble kind of ripple pattern on germanium. On the other hand, the mass effect, 100 kb krypton ions are easily seen to give rise to very mature ripple formation in germanium. 100 kb argon ions can lead to very mature and nice pattern formation on silicon carbide. These are all extremely important material components for device technology. When you talk about high-speed electronic devices, these are extremely important materials. And then I show you the example of gallium arsenide. This is very different case. As I was telling you, when you talk about an elemental semiconductor or a metal, then sputter erosion takes place. But think of a situation when we have a binary material. Means a material having two elements present in it. We saw the examples of gallium arsenide, indiumphosphide, etc. So in those cases, mostly the lighter mass atomic species get preferentially sputtered more. Preferential sputtering means that will be preferred to get sputtered fast ahead of the other heavy mass element present in the same target. That means the other component or atomic species. Now this is very different for gallium arsenide. Here, the preferential sputtering is almost absent because gallium and arsenic both have nearly similar sputtering rate. But still, dot patterns, or in some cases, ripple patterns with clear signature of dot formation at the top of the surface are reported. But then they are very different surfaces as well. One is semi-insulating gallium arsenide, then N-type gallium arsenide. So N-type gallium arsenide and P-type gallium arsenide, mostly we get to see this dot formation as is seen from these two top and bottom frames. One was 50 kb, another is 60 kb, not much different. And 60 kb for P-type gallium arsenide also, we got to see this nano hole pattern at 0 degrees. So very different kind of electrically considered surfaces. The electrical nature are very different. So electronic properties will be very different, although the same gallium arsenide material. You see the same situation for indium phosphide. Okay, it's 100 kb ions. Maybe it's 50 kb ions as well. And these beautiful dot formations take place. Once again, preferential sputtering takes place. So these dots are heavily depleted with one component. Okay. So they are indium rich. Phosphorus gets preferentially sputtered more. Same situation almost for gallium nitride. This nitrogen gets much more preferentially sputtered, giving rise to these dot formation which are heavily rich in gallium. And that was actually observed by high resolution OJ electron spectroscopic measurements. dot size increases with ion fluence. Okay, very clearly, but 25 nanometer was the average dimension here for dots, which turns out to be nearly 3 times more upon increasing the ion fluence by 2 times. And then comes the example of SiO2. We have seen very different results for SiO2 using low energy ions. Okay. Although formation of ripples and surface nanostructures are both common for low and the high energy, I mean intermediate energy like 100 keV argon ions compared to those 500 eV argon ions or 1 keV argon ions. Goes beyond saying that this is the reason for which you get to see much more mature ripples in contrast to those 1 keV ions which were displayed earlier. And I told that this is now published in Journal of Physics Matter, but now this is to be published. Another interesting observation: pattern formation did take place in case of gallium arsenide, that science paper I told you, which actually gave a lot of boom to this field when they used a couple of hundreds of eV or tens of eV, I mean electron volt of argon ions. I mean both in gallium arsenide and indium arsenide. But when we enhance the ion energy from that kind of value of say 100 electron volt or 400 electron volt to 60 kilo electron volt, then we don't get to see any pattern formation. Instead, sponge-like structural evolution takes place, which are highly hydrophobic in nature and highly opaque for the visible light. Okay, so this is another important observation. I talked about focused ion beams. So these kind of patterns, patterns can be premeditated patterns can be programmed, and the machine itself can follow that kind. I mean, produce these kind of patterns. That's very important. So here is an example of a material, a complex oxide, CD2NB2O3, cadmium niobate, at an incident angle of 52 degrees, beautiful ripple patterns were observed. And using 30 kV gallium ions in germanium at an incident angle of 62 degrees, these kind of patterns were observed. Again, we saw that in case of gallium arsenide, very different kind of patterns evolved at tens of keV ion energy. But when we take help of this focused ion beam as a tool to create patterns, we get to see this kind of pattern formation using gold ions, of course, instead of argon. So up to less than or up to 45 degrees, the surface remained flat. Starting from 60 degree to 70 degree, ripple patterns were evolved. Okay. And for incident angle greater than or equal to 80 degrees, the surface again became flat. For which condition? when gold energy was 30 keV per atom. For 15 keV per atom, this is the situation. Even at 80 degree or more, there were ripple patterns. But for 10 keV per atom, one gets to see pattern formation again at angles, incident angles higher than 80 degree. So, very varied kind of pattern formation are reported. Like that, you see indium antimonide using the broad beam, as I told, for both gallium antimonide and indium antimonide. Spongy surfaces evolved. But for focused ion beam, where the incident beam dimension is squeezed up to a couple of tens of nanometer, these kind of beautiful patterns evolved on indium antimonide surface. So there is a huge influence of the ion source, incident ions, and so on and so forth. And this is the case of germanium. So in one case, gallium ions were utilized. In another case, bismuth cluster ions were utilized. And on germanium, beautiful facets were formed. And here honeycomb structures are seen very easily. And fluence was not very high when comparable to the fluences that we have talked about mostly. Now, mostly generic equations like anisotropic Kuramoto-Sivasinski equations, these are nonlinear continuum theory-based equations, and some damping terms are introduced. The Kardar-Paris-Jean equation can predict ripple formation, but they are not directly related to ion-solid interaction. They are more generic in nature, like sand dunes and in the deserts, whatever ripple formations are observed. I mean, they can very well be taken care of by these kind of equations. So linear continuum models. Here, the prerequisite is the surface has to be amorphous in nature. So ion bombardment actually gives rise to such high under such high fluences. This kind of amorphous surface, which we are schematically demonstrated earlier still. So when we talk about ion matter interaction, ion solid interaction, then we attribute pattern formation in general to synergetic effects of both sputter erosion and atomic redistribution due to ion-induced surface diffusion. So in case of surface diffusion, it will change to smoothen the surface from a rough surface, and ion-induced roughening takes place due to sputter erosion. So this is a continuous process. Both are operative. You think of in one case, the surface is getting roughened, but at the same time, ion-induced surface diffusion is trying to kill those roughened part and trying to give rise to, the smoothing touch with respect, in light of the ion-induced diffusion. So small features relax most quickly and small features grow most quickly under ion-induced surface diffusion and ion-induced roughening modes, respectively. There are several theories available to understand how roughness evolves. Okay, and there are two regimes at very high ion fluences. Nonlinear regimes of pattern formation come in picture. Otherwise, in the regime of linear linearity, pattern formed in the linear regime, that means roughness grow exponentially. And several established theories like Bradley-Harper theory, Carter-Vishnyakov theory, solid flow model structure can be stepping in. And for nonlinear regime of pattern formation, exponential growth of roughness breaks down. Wavelength of the ripple shows portioning. And Maki-Cuerno-Barabasi theory or lubrication theory take well care of such, take well care of pattern formation in those regimes. Okay. Now, how long I have, Devasis?
Yes, sir.
Can I have 5 more minutes?
Yeah, you can.
Okay.
Where you can share the test, sir?
Pardon?
Where you can share the test link. When we can share the test.
Sharing is stopped.
Oh, I want to share the test link for a test after your talk or in between your talk.
Maybe just after 5 minutes, I will finish and then you can.
Okay, sir. Okay, sir.
Okay, okay. So when this sputtering takes place, actually, when the atoms get sputtered from surfaces, if they receive energy from incident beam to overcome the surface potential barrier, then only we get to see this sputtering. Okay? So other way around, atoms can get sputtered from surfaces if they receive energy from incident beam to overcome surface potential barrier. Otherwise, what will happen? They will keep vibrating and I will have thermal vibration at being there, remaining in the normal lattice side. Okay. Sorry. And for a planar surface, if we consider that Y is the sputtering yield, J is the ion flux, and N is the atomic density of the target, then the velocity will be can be expressed in terms of this small equation. And what is this velocity? Due to sputtering, the surface recesses with this velocity region. Okay. So slope dependence of sputtering results in the ripple formation. Why? Because as the energy reaches to a point P, look here, okay, due to an ion incident at point P prime, okay, then basically the energy reaching at the point P will be greater than at the valleys compared to the hills. So valleys will be eroded faster compared to the hills, which will result in the growth of surface perturbation, surface instability. On the other hand, as I told earlier also, surface features actually relax due to surface diffusion, that is the smoothing effect. So basically an energy ellipsoid can be thought of, okay, and the energy ellipsoid can be simulated using several freely available simulation codes. This is very important. And here a complex mathematical function gamma xy needs to be considered, which is a complex function of dimensions of energy distribution ellipsoid, like A, sigma, mu, etc. And there will be recoil term also, which is delta. So we can see that the surface height variation can be described by a linear second order differential equation, which takes care of both, which takes care of this competition between sputter erosion and surface diffusion. So this is the ion-induced instability related term along the x and y direction. Sx, Sy is the sputtering coefficient along x and y direction, respectively. And this term corresponds to the surface modeling due to diffusion, ion-induced diffusion. And the solution for the surface height is this. So amplitude of one Fourier mode, kxy, can exponentially dominate all the others. Okay. So the mode KXY actually is observed for periodic ripple structure formation. These are, as I told, these are not so easy thing just to visualize in one go. Okay, but this is just to tell you that how it moves forward also. So these are the mathematical way to show the ripple orientation from the Bradley-Harper model. We have already told you that where the ripple orientation is parallel to this incident beam projection, then it is perpendicular, this parallel mode and this perpendicular mode in the other arm. Okay. And this is how one calculates delta, the recoil from the recoil cascade. Okay. So if one assumes simultaneous contribution of sputtering as well as atomic redistribution due to ion-induced diffusion, surface diffusion rather, then it is found that pattern formation can very easily be explained in most of the cases. And this is one last example of silicon. Basically, the summarizing situation of silicon. I'm showing you here because this is an application. You see very carefully, it's the same results. I mean, divided into two parts. One is the both are parametric phase diagrams where E theta diagram. Basically, these and the y-axis, these are the patterns we observed. Y-axis the ion energy, and along the x-axis the incident angle, ion incident angle, which was varied from 0 to 85 degrees or so for all the energies, and for each incident angle value, we for the same energy, we get to see different surface conditions, surface morphologies, and this is what he has evolved here in the form of what we call it is a parametric phase diagram in the in case of this pattern formation. So what we get to see is a stable surface. That means a flat, stable, flat surface where no patterning was observed. Instability, as I told you, means pattern formation. Instability got set in at 51 degree for all these incident ion energies, and the remains pretty. We got to see parallel mode ripple formation from starting from 51 degree up to nearly 75 degree or so, and then beyond that, at even higher angles, the surfaces became flat again for all ion energies. These are at lower ion fluences, so that's why these are in the linear region. Only parallel mode ripples were formed. Remember, these facets that we saw earlier was an outcome at 72.5 degrees or so in the very early stage. I showed that result. And that is an outcome of nonlinear region. When we go to very high fluences, otherwise, in all all angular windows, either we saw parallel mode ripples or no other patterns. That's in the linear regime. But what we get to see in the nonlinear regime is parallel mode ripples. Then we get to see unusual patterns like needle-like structures or evolution of facets and so on and so forth. And then perpendicular mode ripples. So all these things belong to the nonlinear regime. And these patterns, those evolved in the nonlinear regime, including these ripple patterns, can be very useful for different applications. And that's the reason my second talk will be dedicated mostly with the possible applications of or usage of these kind of pattern surfaces. And on the other end, the entire linear regime part is offers us the best win-win situation to understand the fundamental physics aspect. That means the underlying processes behind the pattern formation process. These are few important issues like reproducibility of patterns across the globe in inter-laboratory. Basically, I do here something, somebody else does at Harvard, somebody else does at in Spain, or somebody does it in some part of Germany or the United States. I mean, whether they mostly have a reproducibility or not. I mean, here and there, we got to see that pattern formation is dependent on a hell lot of parameters, starting from ion energy to ion species to incidence angle, ion incident angle, to flux. I mean, rather the ion flux to ion fluence, and so on and so forth. So that is understandable. Even the ion sources get different parameters actually get changed and so on. So reproducibility of patterns most across the different laboratories throughout the world is very important. And then surface patterning of novel or important materials also has been always a big issue. And I have shared with you as many as possible cases where we can conclude that starting from metal to semiconductor to oxide to polymer surfaces and so on. Polymer, I didn't show the result because it would be lengthier, and but similar results evolve. So take-home message is we can create patterns on majority of the different class of materials, starting from metal to semiconductor to oxide, that means insulators to polymers, and not limited to that anyway, other compound materials also. Impurity-free creation of patterns is actually important. Otherwise, we may land up into very exotic pattern formation, which will be very, very difficult to explain. Okay, and role of ion source is pretty clear, but beam scanning is not clear because in many of these results, particularly done at higher energies up to 50 kV, 60 kV, 30 kV, the beam was uniformly scanned over the surface to enhance, I mean, the completion, sorry, to reduce the completion time of experiments. And then and uniformity also is an issue, of course, because those are millimeter size beam or centimeter size beam. But with the broad beam ion sources which are used for low energy ion patterning, there anyway big uniform beam up to 2 inch or so, it can be easily achieved. 1 inch to 2 inch can be easily achieved. So basically wafer scale integration is directly possible. And over and above, if we can scan the beam to 4-inch wafer, I mean, it's even win-win situation for the industry. And then consistent calculations are needed for those energy ellipsoid, we have already said. And in next lecture, we'll talk about nanoscale functionalities of these pattern surfaces, because creating patterns is one aspect, surface patterning of novel or important materials in the second part. But then what we must think that what do we do with these pattern surfaces, or why do we need to create such pattern surfaces? And then correlation, if any, is also important to know between results obtained from low and medium energy samples. And at the onset, thank you very much for your attention. I know it was never easy to hold everybody up over this long this thing. Understandably, nearly 50% of people have left the meeting also. But nonetheless, I thank you all who were starting from an audience of nearly 68, 69. Still, including myself, 44 of us are present, and so this always keeps the speaker also moving. So thank you very much for your kind attention. And yes, Debasis, if there are questions.
Thank you, sir. I have already shared the test for this session. Sir, actually not left. Actually, there are some people joined for the special lecture by Sangi sir for the national education and policy. That's why they left. Actually,
that's okay. I mean, there's still
whatever registered people, they are already here. Sir. Almost all the registered people are here.
That's fine. But that's what I appreciate. That still 40 plus participants. It's very difficult, Debasis, during this almost approaching lunch time.
Yes, sir,
I mean, in physical meetings, we hardly get to see so many participants. Okay, yes. So that way, still, this shows the power of these online meetings also. So something to lose and something to gain as well.
Yes, sir. Yeah, I already unmuted everyone. If you want, you can ask a question to sir, or you can take your next session there. At that time also you can ask sir, because it's already, we are late almost 15 minutes.
Yeah.
So if you have any question, simple question, you can ask sir to right now. If there are no questions, then we can close the session after a few minutes. Sir,
Yes.
email ID you can find in IOP Bhubaneswar website. Professor Tapobrata Som you can find. Please Google and you can find easily. Sir's email ID. If you are unable to find, we can share here in next session.
Sure.
Any questions from participant side? Yes, I think there are no more questions. So with that, we can close today's session, today's first half session. We will rejoin again at 3 p.m. That is Professor Santanu Jana. His talk is there from Portugal. He will deliver directly from Portugal. So with this, we can close this today's session. Thank you, sir. Thank you all of you.